And question 4. Does there exist a continuous function such that every solution of the differential equation y double prime plus the coefficient at y prime is 1 over 1 plus t squared plus q of t times 0 plus q of t times y equals 0 has the following strange property. And so notice that every solution of the differential equation has this property. There exists a finite limit of y of t, and the limit of y prime of t is 0 as t goes to infinity. Wow. How could we approach such a question? Well, if you look at kind of theorems and facts that you know about general homogeneous differential equations, second order linear, then so notice that it is probably not a coincidence that we are explicitly given the coefficient at y prime, but the coefficient at y is some unknown function q of t, right? Well, and now you start thinking, so did we learn any kind of theorems about the coefficient at y prime? And then you realize, yes, we did, and this is Abel's identity. So Abel's identity is that the coefficient is that the Wronskian is e to the power minus the antiderivative of the coefficient of the integral of the coefficient at y prime. So Abel's formula, well, times some constant, is that the Wronskian of any two solutions is some constant times this integral. So, and since it is more or less the only fact that we know about the coefficient at y prime, then let's try to apply it. So notice that now we don't know whether the answer is yes or no. Okay, so let us just try to reason logically. So suppose that the answer is yes, right? And such a q exists, so which means that there should be y1 and y2 should be linearly independent solutions. So linearly independent solutions. Okay, so if we have a linearly independent solutions, then we have the Wronskian of this y1 and y2, and then according to Abel's formula, this is c times e to the power minus the integral of the coefficient at y prime, which we are given. So it's going to be dt over 1 plus t squared. Well, the antiderivative of 1 over 1 plus t squared is inverse tangent, so this is e to the power minus inverse tangent t. Arc tangent t. All right, so if such a differential equation existed, then it means that the Wronskian of any two solutions would be some constant times e to the power minus inverse arctangent of t. So what does it have to do with our property? There exists a finite limit, okay, blah, blah, blah. Okay, I mean, since we're given some information about y of t and y prime of t, and we know that y of t and y prime of t, they appear in the Wronskian, why don't we just write what the Wronskian is? And the Wronskian is y1 times y2 prime minus y2 times y1 prime. Well, okay, now since we are talking about the limits as t goes to infinity, so let us take the limit as t goes to infinity. Now, so what happens if we take the limit of this as t goes to infinity? So now notice that the limit of y1 is some finite number, say, I don't know, maybe L1. The limit of y2 as t goes to infinity is some finite number, say L2. The limit of y2 prime as t goes to infinity is 0. The limit of y1 prime as t goes to infinity is 0. So then any number times 0 is 0, so which means that the limit of the Wronskian as t goes to infinity is 0. So no matter what linearly independent solutions are, according to this property, the limit of the Wronskian is always 0. At the same time, so let us take the limit of the Wronskian calculated according to Abel's identity as t goes to infinity. Sorry, no, not 0. So as t goes to infinity. Well, the limit of inverse tangent as t goes to infinity is pi over 2. So this is c times e to the minus pi over 2. Well, it is some number. The important point about it is that it is not 0. As long as c is not 0, but c cannot be 0 because we assume that solutions are linearly independent. So since c is not 0, it means that this is not 0. And then we got a contradiction, so that on the left-hand side is 0, on the right-hand side is not 0. So we got that 0 does not equal to 0, and this contradiction shows us that such a differential equation does not exist.